Here's Bullseye Bob holding his rifle in a level position, horizontally. Suppose at the same time he pulls the trigger, he drops a bullet from his trigger hand. Question: which bullet reaches the ground first, the one fired or the one dropped? Let's drop in on my conceptual physics class where I do a demonstration that features this activity.
There's a little device here that will shoot a projectile. Little spring here. I'm going to compress the spring. And when I do that, I can put a projectile here and watch this gang. Little spring gun. Okay. Out it goes. No surprise. But I've got another ball that I can put on the end here like this. And when I go like this, it falls essentially straight down. A little bit out, okay? But kind of downish. This one goes outish. Now I'm going to do them both at the same time. When I do them both at the same time, you guys got to figure out, hey, which one going to hit the ground first? The one that just dropped down or the one that goes out? A lot of people think, oh, the one that's fired out is going to be in the air for a longer time. You know why? The gravity going to start to pull it and say, oh, I didn't know you were moving. Go ahead. And gravity not going to pull so hard. What do you guys think? Let's try it. I tell you what. If you hear this, all A's. All A's. For this course, all A's. Registrar say, Hewitt, my God, Hewitt, you got all A's in your class. I'll say, I had a sharp class, honey. I had a sharp class, all right? All A's. But if you hear this, then you got to do your homework, okay? Here we go, gang. Here we go. This next moment may be very important for a lot of you who have your, everything riding in your grade. All right, here we go. Here we go. Listen. What'd you hear? How many heard this? Wishful thinking. We'll do it one more time in slow motion. All right? Now you can get a better look this time. Slow motion. Here we go. All right? Same time, gang? Yeah. Gravity doesn't take a holiday on an object just because it's moving.
Back to our screencast. So we see that for a horizontally moving projectile, the time of fall is independent of what goes on horizontally. Horizontal and vertical components of motion don't affect each other. That makes sense. If you drop a pencil while standing in the aisle of a fast-moving airplane, the time taken to hit the floor isn't affected by the airplane's speed. Here we have Phil Physiker dropping a ball off the edge of a cliff. A tall cliff. Very tall. We show the positions of fall at 1-second intervals. In the first second of fall, it falls 5 meters. 1 second later, it's 20 meters below the cliff. In 3 seconds, it's fallen 45 meters. And in 4 seconds, the ball hits the ground. It has fallen 80 meters in 4 seconds. Let's pretend there's no gravity and Phil tosses the ball horizontally. We see it travels equal distances and equal times. We're assuming no air resistance. But there is gravity, and the ball falls beneath these points. How far beneath? The answer is, interestingly, just as far as if the ball fell from rest at each point. The positions of the ball would look like this. When we join these points, we find the path of the ball is a parabola. Yum! Let's look at some velocities. First, vertically. An object dropped from rest gains a velocity, v equals gt. G is the acceleration of fall, 10 meters per second square. So in 1 second, its velocity is 10 meters per second. At 2 seconds, 20 meters per second. At 3 seconds, 30 meters per second. At 4 seconds, it hits the ground with a velocity of 40 meters per second. Oops, not enough space to show the full 40 meter per second vector, but I think you get the idea. Suppose Phil throws the ball at 20 meters per second. Then we have a 20 meter per second vector at each of the 4 positions along the green line. All these vectors are equal. 20 meters per second will be the horizontal component of motion along the parabola. We draw 20 meter per second vectors at each position. Next, we draw the vertical components. Again, not enough space for the 40 meter per second component. Then we construct parallelograms for each position. And with the parallelogram rule, we construct the resultant velocities at each position. Again, our lower vector runs off the page, but you get the idea, right? To calculate the magnitudes of these velocities, we use the Pythagorean theorem. V equals the square root of the sum of the components squared. We'll call the horizontal direction x and the vertical direction y. How much is the velocity at the 1 second position? It's the square root of 20 squared plus 10 squared. Your calculator will show you it's about 22 meters per second. How much at the 2 second position? Your calculator will show it's about 28 meters per second. And for the 3 second position? Your calculator will show it's about 36 meters per second. And how fast does the ball hit the ground? Your calculator shows it's very close to 45 meters per second. Once you understand the concepts, calculations can be fun. Yum? Let's take a look at what happens if the ball is tossed at an upward angle instead of horizontally. Watch what happens. Again, we first draw the ball's path as if there were no gravity, a straight line. And we show the positions of the ball for 4 1-second intervals. But there is gravity, so again, the ball falls beneath these positions. How far? Just as far as if dropped from rest at each point. This time our parabola has a different shape. How about if the ball is tossed at a downward angle? Note what happens. Pretty much the same physics. Is this yum or what? Now I want to leave you with a question. Phil Physiker stands on a raised platform and tosses a ball horizontally. The ball leaves his hand a vertical distance of 5 meters above ground level. His friends measure the ball landing 25 meters downrange. So my question is, what is Phil's pitching speed? How fast does the ball leave his hand? And the second question, how fast does the ball hit the ground? 2 questions. Think about them. Until next time, good energy. Phil Physiker tosses a ball across a field. We show sample positions of the ball at 5 locations: A, B, C, D, and E. We draw a vector at position A to show the initial velocity of the ball. At this position, the ball has just left Phil's hand, so no further throwing force acts and remains with the ball. Once out of his hand, the only force on the ball is that due to gravity, and the force of air resistance. To make the physics clear, we'll assume air resistance can be neglected. This vector has two components, a vertical one that changes due to gravity, and a horizontal one that remains unchanged as long as no horizontal forces, such as air resistance, act on the ball. At position B, we draw a shorter vertical component due to the loss of speed going upward. It's shorter than the component at A. But the horizontal component is the same as at A. We construct the resultant velocity vector at this point. At position C, at the top of the path, the vertical component has shrunk to 0. Only the horizontal component remains, which is then the vector for velocity at this highest point. Note that its length is the same as elsewhere. So how fast does the ball travel at the top of its path? 0 if tossed vertically. At other angles, velocity at the top is the same as the initial horizontal component of velocity, and the horizontal component at other positions. At position D, we have much the situation as in B. Same size horizontal component, but with the vertical component directed downward. So the resultant of these components gives the velocity vector at D. Note it's sort of an upside-down image of the situation at position B. And finally, much the same at position E. We're off the page here, but you get the idea. What we have is an upside-down version of A. The shape of the ball's path is a parabola. With air resistance, the path is not parabolic. It's something like this. The horizontal component in each successive position becomes smaller due to air resistance. We just show the horizontal components here. These smaller components are why the ball doesn't go as far downrange. And air resistance vertically means the ball doesn't reach the same height. Interesting? Let's get back to our ideal case without air resistance. The vectors we show are velocity vectors. We could also draw vectors for force, and even vectors for acceleration. Let's draw a vector for the force of gravity acting at the ball, say at position B. Shall we find the resultant of the velocity and force vector, say with this parallelogram? And what would the result be? The answer is nothing with any physics meaning. It would be rubbish. Don't do that. You can't combine velocity vectors with force vectors. They're different animals. To distinguish the two, we show force vectors in red and velocity vectors in blue. Phil Physiker says it well.
Take care with velocity and force vectors on the same diagram. They don't combine.
These red vectors represent the downward force of gravity on the ball all along the path. Although velocity varies along the path, we see that the force of gravity does not. It remains constant. The force vector is the same at all locations. Velocity vectors are one thing, force vectors are another. I want to lead up to a concluding question. We could as well have drawn acceleration vectors in this lesson, but we didn't. And a little thought will tell you that they'd compare well with the force vectors. After all, force and acceleration are directly proportional. Here's my question. What would an acceleration vector look like at the top of the path at point C? What would be the acceleration of the ball at this highest point? Think carefully about that. Until next time, good energy.